All right, so today we're going to look at a few more real world examples of the sine and cosine function graphs. These are called not so simple, but that's not to mean that they're difficult, just means that they are not going to be on the x-axis. These may have vertical and horizontal shifts. So that's the part that's a little bit different than what we did in our previous lesson. So let's take a look. It says, suppose the length of time between consecutive high tides is 12 and a half hours. So time between highs is 12.5. That's already telling us there that our period from high point to high point is 12.5 hours. Okay, it says in Savannah, Georgia, high tide occurred at 3:30 a.m. on June the 28th of 1997, and low tide occurred at 9:45 a.m. So it's giving us a time for a high tide and a time for a low tide. The height of the water at high tide was 13.2 and at low tide 2.2. So we have some points here that we can graph. So let's do that. We know that our height in our water, so our height we're going to put on our y-axis, 13.2 for the high point, and the time for the high point was 3:30 a.m. So I'm going to come out here 1, 2, 3. So 3:30 a.m. is going to be between 3 and 4. So actually at 3.5. That's my high. All right. And then it says the low tide was at 2.2 feet. So that's still a positive value. So I'm going to put 2.2 in here. And the time for that was at 9:45 a.m. So 4, 5, 6, 7, 8, 9, 10. So 9:45 is going to be right in here. And that's going to be my low point. Okay. Now I know that I need to keep going out here until I get back up to my high point so that I can draw my graph. Right. Now I already know that the distance in between my high points is 12 and a half hours because it told me that in the problem. So I have a lot of useful information here. Now, if you wanted to put these as decimals, this would be 3.5. 9:45 is going to be 9.75, right? I know that between 3:30 and 9:45, if I wanted to continue going out here to my next high point, I probably need to go out to, what would that be, 16? I need to double that amount to get out to my next high point. Or just go 12 and a half hours. 3.5 plus 12.5 would be 16. So 16 hours out and I'm back at my high point. But you don't even have to know this. You don't have to put that on there. Everything that you needed was given to you in that first information. All right, so what we need to do to write our equation is to find our amplitude, our B value, our left-right shift. So we'll just do H and K, and our up-down shift. All right, so amplitude. Well, the amplitude is the middle of the road line here. It's how high and low we go off of that middle line. So we haven't really been dealing with the formula much. We've just been eyeballing the graph. Since this graph was drawn by us and we're not sure exactly where that is, we can just subtract and then split it in half. So 13.2 minus 2.2 and then divide it by 2. So, no, sorry, plus. These are both positive. sorry, no, I was right the first time. High minus low, split in half, so that would be 11 over 2, which would be 5.5. So my amplitude is 5.5 units above and below. Now, if I want to find out where this line is so that I know what the axis, where that axis has been translated, then I could just take this 5.5 and add it to 2.2. So that would put me at 7.7. So this is 2.2 plus 5.5 gives me my 7.7. That tells me how far it's been shifted up, translated up. So that's going to be my K value. For the B value, it's 2 pi divided by our period. Now, I don't normally like decimals inside of fractions, but we have a lot of other things to deal with. So if you want to leave it 2 pi over 12.5, I'll take that. Or if you would like to double it, this is the same as 4 pi over 25, but again, you don't have to worry about that. And then the height, the H value, which is going to be our left-right shift, that's going to depend on where we want to write our equation. Now, since the first thing they gave us was a high point, then I'm going to write this as a cosine equation. And as a cosine equation, the first high point is at 3.5. So 3.5 to the right. If you wanted to write this as a sine graph, you would need to figure out where this point is, which is a whole lot more work. So I would just use the information given to us. So that's everything we need to write our equation. So we have y equals our amplitude, 5.5, cosine graph, our b value, 2 pi over 12.5, or if you want to use the 4 pi over 25, and then our left-right shift, so minus 3.5, and then up 7.7. So because a lot of these are real applications, the numbers aren't quite as clean cut as we'd like, but still they're the same as if they had been whole numbers. Just don't let the decimals throw you. Once we have our equation written, then we can answer questions about this graph. So the first question says, when did the next high tide occur? We actually already have that because we talked about this number out here. The high tide to high tide would be our period. So remember this 3.5 plus 12.5 was 16. So 16 hours out. So, time-wise, we started this one at, let's see, at midnight. Midnight was our origin. And so if we start at midnight, we go all through the day. Once we hit 12, that's 12 noon. So 16 would be at 4 p.m. All right. What was the water level at 11 p.m.? Well, 11 p.m., that's going to be an X value. That is before midnight, so we don't have to worry about any kind of changes to that. 11 is just going to be when we reach 11 p.m. on that day. Oh, yes, so we do need to make changes. 11 p.m. because these were a.m. So we started at a.m., 1 a.m., 2 a.m. So once we get out here to 12, then we need to add 12 plus 11. This is actually at 23 hours out. So it's the 12 plus the 11 additional hours. This is from midnight to noon. Midnight to noon. And then afternoon, we went 11 more hours. So that's where this 23 comes from. So at 23 hours out, we want to type this into our calculator. Okay, so here we go. We type this in. Again, this is one that has a shift on it. So what I was saying in an earlier lesson, we want to, when it opens the parentheses, go ahead and put your B value, but then put an extra set of parentheses for your left-right shift and close them both out before you place your up-down shift at the end. So here's our equation. It's asking us about what's going on when at 11 p.m. or when x is 23. So we're going to second calculate the value when x is 23. Oh, I see what my problem is. I didn't even show you guys this. I went from 0 to 16 because I wanted it to match my paper, 0 to 16 on my x. And for my y, I went 0 to 14. I kind of went a little past 13, and because it was a decimal. But I just asked it a value that was greater than 16. And so I'm going to need to change this to like 24. So now then, when I calculate the value, it's going to change my graph up a little bit, show me a little bit more, but I can type in 23. So I have 2.586. All right. So if they give me an x value, then I can just second calculate the value. If they give me a y value, then just like we did before, we would put in to y equals. All right, in our second example, it says, since the number of hours of sunlight in a day cycles annually, it can be modeled with a sinusoidal function. The longest day of the year occurs on the summer solstice, while the shortest day of the year on the winter solstice. So we've got a long day and a short day. Summer solstice, winter solstice. So it says in Boston, the number of hours of sunlight on the summer solstice, so the longest day is 15.283 hours of sunlight. The winter solstice, the shortest day, is 9.067 hours of sunlight. Now it's telling us when the winter solstice occurs, day 355. So let's go ahead and plot what we have. We know that our highest number of hours is 15.283. Our lowest is 9.067, and this is hours of sunlight. All right, and we know that this one, this 9.067, occurs on day 355 of the year. So 355, no, there's only 365 days in the year, so 355 is going to be close to the end of the first year for our short day. But anyway, we're going to go ahead and mark that point. That's our shortest day. It's during the winter time. We have short days during the winter. And we know that there are 365 days in the year. So I know that somewhere back over here, there's going to be a long day, and that same distance out on this side, there's going to be a long day again. And I know the difference between the longest days, or I could have gone from low day to low day, is 365 days. So our period is going to be 365. So let's see what all we have with just that information from what they gave us, and then we'll see if we need to figure anything else out in order to write our equations. So we know we need our amplitude. So it's our high point minus our low point divided by 2. All right, so here it is, high point minus low point, and then split that in half, so we get 3.108. All right, so that's going to be our amplitude. So if I were to add that to 9.07, so 3.108 plus our low 9.067 puts me at 12.175. So this middle line that's always important to us to write the equation is at 12.175. So that's going to be my K, my up down shift. All right. Now our B value is always 2 pi divided by our period, in this case 365. And so the only thing we need now is our up down shift. I mean our left right shift, which in this case the one thing that we do know is right there at 355. So if you don't want to figure anything else out, you can use this 355, and we'll write this as a cosine graph because it starts at a low point. I guess I shouldn't put equals. So if we write this as a cosine graph at 355 to the right, the only thing we need to remember is that the graph has to be reflected because this thing is starting down low. Instead of starting up high at 355, it starts low, so it's a reflected graph at 355. So that would be enough for us to write an equation without finding any other information about our graph. So here we go. Y equals our amplitude, 3.108, but if we use that 355, we have to make it negative. Cosine, our B value, 2 pi over 365. Our left-right shift, x minus 355, and then add our up-down shift, 12.175. Erase it and write it again, 12.175. All right, so that's our equation. So now they're going to ask us questions about this graph, and we should be able to get the equation to answer them. All right, so it says enter the function into the calculator. We're going to answer our equation, or answer our questions. All right, so here is our equation. Negative 3.108 cosine. It's going to open parentheses, 2 pi over 365, open a new set of parentheses for our left-right shift, x minus 355, close them both out, plus our up-down shift, 12.175. Okay, so for our window, I went 0 to 365 and changed my scale to 10 so there wouldn't be quite so many marks. My y-axis, I went 0 to 16, but I am going to point out that since I only went to 365, I'm only going to right in here, and so it's going to show, you know, all the things that are going on over on this side of the graph that I didn't even sketch. So when I type it in, it's not going to graph exactly what I have in my window, because this over here is my 355. So this is everything that's happening before 355. So I mean, you could make adjustments to that if you'd like, but I think that one year is probably enough to answer our questions. So here we go. Our questions say, how many hours of sunlight were there on September 20th? And they were very nice to us to tell us that that is day 365, or x is, I'm sorry, 263. That way we didn't have to count how many days there were between January 1st and September 20th. So when x is 263, we're going to second calculate the value at 263, and it says that there's 12.215 hours. So quite a few hours of sunlight on that day. Now on March 1st, which is day 60, so second calculate the value, and x is 60. We get 11.063 hours of sunlight. So both of those days fairly long. It says when are there at least 12 hours of sunlight to the nearest day? Well, there were 12 on that day, not on that day, but 12 hours of sunlight is a Y value. Hours of sunlight is a Y value. So they're asking us for what days is Y at least 12. So we're going to go into our Y equals, and then Y2 put in 12, and we get this line going across here. Any of the days that fall in between here and here have more than 12 hours, right? These are less than 12. These are more than 12. So we're going to find these two intersections, and that will be our solution. So second, calculate the intersection. All right, so that one is at 77.977, so about day 78. And the other intersection is 267, so day 267. So between day 78 and days 267 of the year, there are at least 12 hours of sunlight. Now, if you wanted to know exactly what those days of the year are, you could use what they gave us to kind of to get that answer a little more quickly than actually counting the days from January 1st. If we know that March 1st is day 60, then day 78 is 18 more days later, or March 19th. And day 267, that's 4 days after day 263, so that would be to September 24th. So date-wise, March 19th to September 24th in Boston are going to have at least 12 hours of sunlight. But I would accept this answer as well, day 78 to 260.